What if I told you that the single greatest computational revolution in human history is already underway, but almost everything we think we know about its destiny is wrong? We've all been sold a very specific, very seductive dream. That one day, godlike quantum computers will awaken, and with their near-infinite power, they will train our artificial intelligence models in the blink of an eye. It's a story of ultimate succession, the quantum king overthrowing the classical GPU. But what if the throne they are destined for isn't the one we overbuilt? What actually gives a quantum computer its power? And is it even the kind of power AI truly needs? Today, we're going to untangle the hype from the hardware and ask a question that might just redefine the next century of technology. We begin with that powerful, pervasive belief. It's a headline you've probably seen a dozen times, a promise whispered in tech circles and investor meetings alike. Quantum computers are coming to supercharge AI. The idea feels intuitive, almost like a natural law of technological progression. We have classical computers. They're getting faster, but we're hitting physical limits. Along comes this new, almost mythical form of computing that leverages the bizarre rules of quantum mechanics. Surely, its destiny is to pick up where our current technology leaves off, to take the torch from our silicon chips and carry it into a new dawn of intelligence. The assumption is that faster is the name of the game, and that a quantum computer is simply the ultimate speed machine. But this is where the story gets complicated. To understand the future, we have to first understand the monumental scale of the present. Let's ground this in reality with a true titan of modern AI, Meta's Llama 3.1. This isn't just a clever chatbot. It's a universe of information, a digital brain of staggering complexity. We measure its size in parameters, which you can loosely think of as the knobs and dials of the neural network, the individual connections that learn and store information. Llama 3.1 has 405 billion of them. That's more than 4 times the number of stars in our Milky Way galaxy. But a brain is useless without experience. It needs to be trained on data. Llama 3.1 was fed a diet of 15 trillion tokens of information. Think of a token as a word or a piece of a word. This is a library of text so vast it would take a human thousands of lifetimes to read. Now, let's talk about the cost of that education. If you were to train this colossal model on a single, top-of-the-line GPU, the workhorse of the AI world, it would take an estimated 4,486 years. Let that sink in. A single machine, running non-stop from the time the Roman Empire was crumbling, might just be finishing the job today. This is the computational Mount Everest that AI developers are trying to climb. So how on earth did Meta train it in just a few months? The answer isn't a better single computer. It's a better system. The secret is a concept that is both simple in theory and breathtaking in practice: parallel computing. Instead of asking one genius to solve an impossibly large problem, you break the problem down into millions of smaller, manageable tasks and give them to an army of competent workers to solve all at the same time. This is precisely what a graphics processing unit, or GPU, is designed to do. While a central processing unit, CPU, in your laptop is like a master chef, incredibly skilled at performing complex, sequential tasks one after another, a GPU is like a massive kitchen staffed with thousands of line cooks. Each cook might only be able to do a few simple things: chop an onion, stir a pot, but they can all do it at the exact same time. When training an AI model, the cooking involves countless simple, repetitive mathematical calculations. By stringing together thousands of these GPUs into massive supercomputers, companies like Meta, Google, and OpenAI create a computational army. They take that 4,500-year problem, slice it up, and distribute the workload. That's how you shrink millennia into months. It's a triumph of brute force, hyper-efficient parallelism. It's the engine that powers the entire modern AI industry. And this is where our story pivots. We've just seen how an army of thousands of processors working in parallel can conquer a problem of immense scale. So, the natural next question is, what happens when a new type of processor enters the battlefield? We look at this incredible leap from single-core CPU to massively parallel GPU, and we instinctively project that same logic forward. If a GPU is 1,000-line cooks, a quantum processing unit, or QPU, must be 1,000,000, 1,000,000,000, an infinite number of cooks, right? Could a single quantum computer offer a leap so profound it makes a warehouse full of GPUs look like a child's toy? This is the heart of the matter. We're asking if a quantum computer can not just join the army, but replace it entirely. Can it parallelize computation on a level that is fundamentally, unimaginably greater than what we have today? To answer that, we need to get our hands dirty and look under the hood of an AI model. What are those thousands of GPUs actually doing for months on end? The answer, overwhelmingly, is one thing: matrix multiplication. It might sound like something from a high school math class, but this operation is the fundamental building block of neural networks. Every time an AI processes information, whether it's learning from text or generating an image, it is essentially multiplying enormous tables of numbers, matrices together, over and over and over again. These matrices represent the input data and the weights of the neural network's parameters. The entire learning process is a relentless cycle of multiplying matrices to make a prediction, checking how wrong that prediction was, and then nudging the billions of parameters in the right direction through more matrix math. This is the true computational bottleneck. It's the shovel work of intelligence. We measure this work in a unit called flops, floating point operations per second. It's a direct measure of how much raw number crunching a processor can handle. So, how many flops does it take to train Llama 3.1? The numbers become almost comically large. To process 15 trillion tokens through a 405 billion parameter model requires roughly 10^25 floating point operations. That's a 1 followed by 25 zeros. It's a number so vast our brains have no intuitive reference for it. It's 10 septillion calculations. This number is the benchmark. This is the mountain. For a quantum computer to be a viable replacement for training large language models, it doesn't just need to be fast. It needs to be able to perform or somehow bypass this astronomical amount of matrix multiplication. It has to compete on this specific battlefield, a field defined by a very particular kind of mathematical brute force. This brings us to the most common and most dangerous misconception about quantum computing. We often hear that thanks to a principle called superposition, a qubit, the quantum version of a classical bit, can be both a 0 and a 1 at the same time. Extrapolate that, and a quantum computer with hundreds of qubits can explore a vast number of possibilities simultaneously. This leads to the seductive but flawed conclusion that it can do all the calculations at once. Imagine you're trying to find the right key to open a lock. A classical computer would be like trying each key on a keychain one by one. The quantum myth suggests that a quantum computer can try every single key at the exact same instant, instantly finding the right one. But this oversimplifies quantum mechanics to the point of being fantasy. While a quantum computer can explore a massive problem space simultaneously, it's not a magic bullet. The act of measuring the result, of getting the answer out, collapses that beautiful quantum state into a single, probabilistic classical answer. The true genius of quantum computing lies in designing algorithms that cleverly use quantum interference to make the wrong answers cancel each other out, and the right answer more likely to appear upon measurement. It's not about doing everything at once. It's about a carefully choreographed quantum dance that guides you toward a solution. And it is not at all clear how this dance maps onto the brute force matrix math that AI training demands. So let's return to our analogy. The leap from CPU to GPU was a leap in parallelism. A CPU is a master architect, designing the whole building. A GPU is the massive construction crew that can lay 1,000,000 bricks at once. Both the architect and the crew are working with the same fundamental materials. Bricks and mortar, or in our case, binary zeros and ones. They follow the same laws of physics. The proposed leap to a QPU is different. It's not just a bigger construction crew. It's like a crew that builds with clouds and lightning instead of bricks and mortar. They operate under a completely different set of rules. We can't just hand them the same old blueprint and expect them to build the same house faster. The very logic of construction has to change. So, the question remains. Is the QPU an extension of the same logic, Or is it something else entirely? Here we arrive at the most crucial distinction. A CPU and a GPU are both binary and deterministic. They store information as definite zeros or ones. If you give them the same input and the same instructions, they will produce the exact same output every single time. 2 plus 2 will always equal 4. This reliability is the bedrock of all classical computing. A QPU is fundamentally different. It is probabilistic. Its basic unit, the qubit, exists in a superposition of states. When you measure it, you get a 0 or a 1, but the outcome is governed by probability. It's like a rigged coin flip. A well-designed quantum algorithm can rig the coin so it almost always lands on the answer you want, but the inherent uncertainty never truly goes away. This isn't an evolutionary step, like moving from a 4-cylinder engine to an 8-cylinder engine. This is a revolutionary leap, like moving from an engine to a sail. One uses controlled explosions of gasoline, the other uses the unpredictable currents of the wind. You can't just drop a sail into a car and expect it to work. The entire architecture, from the ground up, is built on a different philosophy of processing information. This architectural divide creates a massive, practical roadblock that is rarely discussed in mainstream articles: the encoding challenge. Remember Llama 3.1's 15 trillion tokens of training data? That's all classical deterministic data, text files, images, code, stored as trillions of zeros and ones. To use a quantum computer, you first have to translate this mountain of binary data into the delicate, probabilistic language of qubits. This is not a simple one-to-one mapping. How do you represent the word love or a picture of a cat in a quantum state? How do you load a 100 gigabyte dataset into a few hundred qubits without losing all the information? This is one of the biggest open research questions in the field. Current methods for encoding classical data into quantum states are incredibly inefficient. In many cases, the computational cost of just getting the data into the quantum computer in a useful way could completely erase any potential quantum speedup you hope to achieve. It's like having a supercar that can go 1,000 miles per hour, but it takes you 3 weeks to buckle the seatbelt. You might be thinking, well, can't we just map a classical 0 to 1 quantum state and a classical 1 to another? This is what we could call the naive approach. You can certainly do this, but in doing so, you completely miss the point of quantum computing. If you constrain your qubits to only ever be in a definite 0 state or a definite 1 state, you're not using superposition. You're not using quantum entanglement. You're essentially using your fantastically complex and expensive quantum computer as a very, very bad classical computer. You've brought your sailboat into the garage and are trying to rev its engine. You've ignored the very properties, superposition and entanglement, that granted its power in the first place. The real advantage comes from letting the qubits explore the infinite space of possibilities between 0 and 1, and this simple mapping throws that entire advantage away. This forces us to take a step back and look at the situation with clear eyes. On one hand, we have a problem: training massive AI models that requires trillions of very specific, deterministic mathematical operations. On the other hand, we have an existing solution, massively parallel GPUs, that is custom-built to solve this exact problem with incredible efficiency. It's a system that works, and it's getting better every single year. So, when we propose using a quantum computer for this task, we have to be honest. We are proposing to replace a highly optimized, purpose-built tool, the GPU, with a revolutionary, paradigm-shifting new tool, the QPU, that is, by its very nature, ill-suited for the specific, brute-force task at hand. It's like trying to use a delicate surgical scalpel to demolish a building. It might be an incredibly advanced tool, but is it the right tool for this specific job? The evidence so far suggests maybe not. This realization is not a defeat for quantum computing. It's a clarification of its purpose. The most brilliant researchers in the field are no longer naively asking, how can we replace GPUs for training LLMs? Instead, they are asking a much more interesting and profound question. What are the problems within the vast landscape of AI that are fundamentally quantum in nature? Perhaps the role of a QPU isn't to do the same job faster, but to do entirely new jobs that classical computers can't even begin to attempt. This could mean designing new types of machine learning models that are inherently probabilistic, perfectly matching the hardware. It could mean solving complex optimization problems, like finding the perfect drug molecule or creating new materials for batteries, problems where exploring a vast landscape of possibilities is key. It might not be about training the AI, but about giving the AI fundamentally new and powerful tools to solve problems with. Instead of replacing the GPU army, the quantum computer might become the elite special forces unit, called in for missions no one else can handle. Let's bring back our CPU-GPU analogy one last time, because it provides a powerful historical lesson. When Nvidia first introduced the GPU for scientific computing, many people in the CPU-dominated world were skeptical. They saw it as a niche tool for making video games look pretty. But something interesting happened. The CPU didn't disappear. Your computer still has one. The CPU and GPU found a symbiotic relationship. The CPU remains the master controller, the brain of the operation, handling all the complex, sequential tasks it excels at. The GPU became the specialized workhorse, handling the massive parallel workloads it was designed for. They coexist, each playing to its strengths. Perhaps this is the true path forward for the QPU. It won't replace the GPU, just as the GPU didn't replace the CPU. Instead, we might see a future of hybrid computation, where a classical supercomputer handles the data processing and large-scale training, but it can call upon a QPU as a specialized coprocessor when it encounters a problem with a quantum-native structure. Each technology will find its own niche, its own place in the ecosystem, making the whole system far more powerful than the sum of its parts. This brings us to the cold, hard reality of business. In a world where companies are spending billions of dollars on GPU data centers that deliver tangible results today, the argument for quantum computing has to be more than just a futuristic promise. There is healthy skepticism. Why should a company invest hundreds of millions into a technology that might not be able to train their core AI products when they can spend that same money on more GPUs and get a guaranteed, predictable return on investment? For quantum computing to move from the research lab to the real world, it needs to find its own viable market. It needs a killer app. That one application it can perform so much better than any classical computer that it becomes indispensable. The pressure is on not just to build better quantum computers, but to find the right problems for them to solve. Without a clear market and a clear advantage, it will remain a fascinating but commercially stagnant technology. And yet, there's a strange and powerful irony at play. The very AI boom that is solidifying the dominance of classical GPUs might also be the economic engine that saves quantum computing. The explosion of capital and investment into AI is unprecedented. Trillions of dollars are flowing into building the future of intelligence. While most of that money is going towards GPUs and infrastructure, a portion of it is being allocated to high-risk, high-reward moonshot projects. A company that has already cornered the market on classical AI might be the only one with enough capital and foresight to invest in the next paradigm. They see the writing on the wall. The insatiable demand for computation will eventually require new solutions. The AI boom could provide the financial fuel to get quantum technology through its long, difficult development phase, keeping the dream alive long enough for it to find its place. If the two technologies can find a way to align. No one understands this dynamic better than Jensen Huang, the CEO of Nvidia. In interviews, he has often reflected on the early days of his company. When Nvidia was championing the GPU, the world was dominated by CPU giants like Intel. It was a massive, risky bet on a new kind of computing architecture. They had to fight for years to prove its value outside of gaming, creating new programming languages like CUDA to even allow developers to access its power. Huang's story provides a perfect historical parallel for the quantum companies of today. They are the new upstarts, betting the farm on a revolutionary architecture that the incumbent powers don't fully understand or see a need for. The path is incredibly risky, fraught with technical and financial challenges. But Nvidia's success is a testament to the fact that these paradigm shifts can happen. It proves that a company with the right vision and the tenacity to build not just a new chip, but an entire ecosystem around it, can fundamentally reshape the world of computation. The question is, which of the many quantum startups today will be the Nvidia of tomorrow? So, After all this, is the hype around quantum computing justified? It's a fair question. For decades, we've heard that a quantum revolution is just around the corner. Yet despite billions in investment, there are still very few, if any, real-world problems where a quantum computer has definitively beaten a classical one. The hype is justified in one sense. The potential of the technology is truly transformative. It represents a fundamental shift in our understanding of computation and the universe. The excitement in the scientific community is real and well-earned. But the hype can become dangerous when it sets unrealistic expectations for the timeline and the applications. Quantum computing is not a faster horse. It's the blueprint for an airplane. And right now, we're still figuring out how to build the wings. Part of the confusion comes from the word scaling. In the classical world, we think of Moore's law. The number of transistors on a chip doubles roughly every 2 years, making computers exponentially more powerful. We instinctively try to apply this logic to quantum computers, thinking that scaling just means adding more qubits. But scaling in the quantum world is a multi-dimensional challenge. It's not just about the number of qubits. It's about their quality. How stable are they? It's about their connectivity. How well can they talk to each other? And most importantly, it's about error correction. Adding more qubits is useless if it also means adding more noise and errors into the system. It's like trying to build a taller and taller skyscraper on a foundation of sand. The challenge is not just to scale up, but to scale up reliably. Today's most advanced quantum systems have hundreds, and in some cases, over 1,000 qubits. This sounds impressive, but these are what we call noisy intermediate scale quantum (NOSQ) devices. They are incredibly sensitive to their environment. The slightest vibration or change in temperature can disrupt their delicate quantum states, a phenomenon called decoherence. This instability leads to high error rates. While a classical computer might make one error in a quintillion operations, a quantum computer might make an error in every few hundred or thousand operations. This makes running any long, complex algorithm practically impossible without robust error correction, something that is still in its infancy and may require millions of physical qubits to create just a handful of perfectly stable, logical qubits. We can build impressive engines, but we haven't yet figured out the cooling systems to keep them from overheating. Crucially, these errors aren't just bugs in the code that you can patch. They are a fundamental consequence of the probabilistic nature of quantum mechanics. You are working with probabilities, not certainties. This demands an entirely new way of thinking about algorithms. A quantum algorithm designer can't just write a set of instructions. They have to choreograph a delicate dance of probabilities. They have to design computations that are inherently resilient to noise, that can somehow guide the chaotic quantum system toward a useful answer despite its flaws. This is an immense intellectual challenge, and it means that the hardware and the software must be co-developed in a way that classical computing never required. To make matters even more complex, there isn't just one way to build a quantum computer. It's not like the PC market, where everyone generally agrees on silicon-based transistors. The quantum world is a Cambrian explosion of competing hardware approaches. Some researchers use superconducting circuits, cooled to temperatures colder than deep space. Others use trapped ions, holding individual atoms in place with lasers. There are approaches using photonics, particles of light, silicon quantum dots, and neutral atoms. Each of these methods has its own unique set of strengths and weaknesses when it comes to challenges like coherence, how long a qubit can hold its state, scalability, how easy it is to add more qubits, and gate fidelity, how reliably you can perform an operation. We are in the very early days, and it's not yet clear which, if any, of these technologies will ultimately win out. It's a thrilling horse race, and the outcome will shape the future of the entire field. But for all these immense challenges, there is an equally immense opportunity. Because nothing is settled, everything is up for grabs. This is a field where a brilliant graduate student in a university lab could, in theory, invent a new type of quantum gate or design a novel algorithm that changes everything overnight. For the early innovators, the builders, the thinkers, this is the frontier. This is a rare moment in history where the fundamental paradigms of a major scientific field are still being written. The opportunity is not just to build a better computer, but to invent entirely new ways of thinking about information, reality, and computation itself. It's a chance to lay the foundational stones for a century of future technology. And so, we arrive back at our ultimate question, but now with a much richer, more nuanced understanding. Will quantum computers revolutionize AI? Or should they focus their incredible power elsewhere? The answer is likely both. The dream of using a quantum computer to train the next Llama model seems, for now, to be a misapplication of the technology. That domain, for the foreseeable future, will likely belong to the ever-scaling armies of classical GPUs. They are the right tool for that job. But the true revolution may come from quantum computers, unlocking entirely new frontiers of knowledge alongside AI. Imagine an AI that, when faced with a problem in drug discovery, can send that specific molecular simulation problem to a quantum coprocessor. The QPU solves that one piece of the puzzle, the piece that is quantum in nature, and feeds the answer back to the classical AI, which then incorporates it into its broader understanding. Will LLMs remain a GPU domain? Probably. Will quantum computing unlock new paradigms of problem solving that we can barely even conceive of today? Almost certainly. The future isn't a story of replacement, but of partnership. It's a story of finding the right tool for the right job, and in doing so, building a computational ecosystem far more powerful and diverse than we ever imagined. The journey through the quantum realm teaches us a powerful lesson that applies far beyond technology. We often get fixated on a single, linear path of progress, making the thing we already have simply faster or bigger. But true breakthroughs often come from stepping off that path entirely and asking if we're even using the right tools or asking the right questions. It's a reminder to challenge our own assumptions, to understand the fundamental nature of our problems before we rush to a solution. Sometimes, the most powerful tool isn't the one that does the old job better, but the one that enables us to do a completely new job we never thought was possible. So, what do you think? Where will we see the first true, undeniable quantum advantage in the real world? Will it be in medicine, finance, materials science? Let me know your thoughts down in the comments below. Thank you so much for joining me on this deep dive. I hope it's given you a new perspective. Take care of yourselves, stay curious, and I wish you all the best of health. If you enjoyed this journey and want to explore more of the frontiers of science and technology, please consider subscribing to the channel. We have a lot more to discover together.